Welcome to Semantic Web Technologies. Lecture 4, Knowledge Representations. This is part 6, Canonical Forms. In the last parts of the lecture, we have learned about propositional logic and first-order logic. And also we have heard about description logics and about the foundations of logic. And one really important thing are so-called canonical forms. Why do we need canonical forms? Just simply because for every formula, there exist infinitely many logical equivalent formulas, as you can see here on that table of equivalencies. Let's go through these equivalencies. So on the first two formulas, you see simply an equivalence where the variables can be exchanged for conjunction or for disjunction. So this is the so-called commutative law. On the next one, you can see equivalencies between implication and disjunction, as well as equivalence can be expressed as two implications. So it's simple, F is equivalent to G only if F implies G and G implies F. So that's pretty simple. Let's take a look at the next one. These two are the so-called De Morgan's law. They are called after the mathematician Augustus De Morgan. So what you can do here is you can put the negation that is in front of this expression inside the braces. So you can put it directly in front of the variables here. So you have here not and then F and G, and this equals not F or not G. And vice versa, you have here not F or G, and this equals not F and not G. So what you do by applying De Morgan's law is you switch between conjunction and disjunction or vice versa. And the second thing is you also change the negation and the position of the negation. The next thing also you might have seen before, this is a double negation, and a double negation then inverts itself. So double negated F equals F. Then let's take a look at this one. T and F in small letters here means true or false. So a conjunction with a truth value true, of course, then equals to the original value of the variable. On the other hand, a disjunction with the truth value true, of course, is always true. And on the other hand, a conjunction with the truth value false will be false, and a disjunction with the truth value false will be the value of the original variable f that you have here. And on the other hand, of course, f and not f always computes to false, while f or not f computes to true. Let's take a look at the next one. What you see here is you can put in this disjunction or this conjunction the variable that is in front of the braces here into the braces. So here you have f or g and h, where g and h are in braces. This equals to f or g and f or h. So f is applied to both of the variables inside the braces, and it's the same for the conjunction here. So this is the distributive law. So it's getting more interesting now here, because here we are definitely then in first-order logic, because you see here quantifiers. And also for quantifiers, there are certain equivalences that have to be considered. So for example, here we have a negation in front of the quantifiers. And often you want to put the negation inside the bound formula, the formula that is bound by the quantifier. So not for all x is f is the same as there exists an x for that holds not f. On the other hand, not there exists a variable f, x that holds f equals to for all x it holds not f. Okay, let's go one step further. Of course, when you have the same quantifiers over several variables, then you also can exchange their position. This holds for the universal quantification as well as for the existential quantification. And what you see here, again, you have the quantifier in front of a formula that is given in braces. You can put the quantifier into the braces, and then, of course, if you have the formula for all x, it holds that f and g, this is equivalent to for all x it holds f, and for all x it holds g. So pretty simple. But with quantifiers, you have to be careful. You can see this on the next slide, because quantifiers of the same sort, as we have seen, they are commutative. But if you consider quantifiers that are not of the same sort, then the same not holds. So because if you have here an existential quantification over the variable x, and then you have a universal quantification over the variable y for the formula f, this doesn't mean the same as if you would switch and turn around these two quantifiers. We can this make clear with a simple example. So let's consider here the first one. Here we have this sentence, there exists somebody, means a variable x, who loves everybody. So for there exists a variable x, and for all variables y, it holds that x loves y. If you translate this in natural language, it means there exists somebody who loves everybody. Vice versa, there's completely different sense, because then you have everybody, it means all y, is loved by somebody. So everybody, it means all variables y, and there exists a variable x for which it holds that x loves y. Everybody is loved by somebody. And this is clearly something different to there exists somebody who loves everybody. You see, you must be careful here. Okay, and now all of these equivalence classes, it's difficult when they can express the same knowledge to find a true equivalence, because the same knowledge or the same formula with the same truth value can be expressed in various different ways. And therefore, you need a unique and standard way to express a given Boolean formula. And this standard way, or this normal form, as it is called, is a so-called canonical form. You do this simply, for example, to save here lots of negations. So you can here remove each double negation. So for example, we write not f instead of not f, which is an uneven number of negations. Therefore, you can eliminate the first 4 in that row. So then if we find a unique equivalence, a representative for the equivalence class for all formulas that represent the same notion or the same knowledge, then we will end up in a canonical form, and then it is rather simple to compare two given formulas. Because what you do then is, you have one formula and another formula, you transform both of these formula into the canonical form, and then you can do a simple syntactic match to see whether they compute the same value. So this is pretty simple. Okay, now we consider as a canonical form the so-called conjunctive normal form or clausal form. A conjunctive normal form simply is a conjunction of disjunctions, as you see here. And this can also be represented as a clausal form. So what is a clausal form? A clause itself is nothing else but a finite disjunction of literals. And the literal might be a positive or a negative variable, for example. So here you see a clause, so it's simply a disjunction. And you can write this also by neglecting the operator and simply writing in these curly braces the single literals. And then instead of the comma you see here, you interpret the comma as a disjunction. Then a conjunctive normal form, as we know, is also abbreviated as CNF. This is a conjunction of clauses, and therefore a clausal normal form corresponds to such a conjunctive normal form, and you can write this here in double curly braces as you see here. So pretty simple. So it's only for simplification. Just imagine that instead of the commata, there would be conjunctions and disjunctions, and you know how to transform this. And it's much more easier to read than if you have complex formulas given. And then later on, in a later part of the lecture, we will come to the so-called technique of resolution, where we will define an automatic way, or learn about an automatic way to deduce or to infer whether a given formula or knowledge base contains a contradiction, or if there is a satisfying assignment for that knowledge base. And this technique relies, for example, on this clausal form, and is much more easier done with this clausal form. But we will come to that later. So, how do we transform an arbitrary formula into a canonical form or into a clausal form? For first-order logic, you need 4 different steps. And all these single steps define a special normal form, and the last one is the conjunctive normal form or clausal form where we're trying to go to. So the first is the so-called negation normal form. There we try to move all negation mostly inwards the formula. Then we have the prenex normal form. There we try to move all quantifiers in front of the formulas we have. And then we have the so-called Skolem normal form. There we try to remove all existential quantifiers. And then if you only have universal quantifiers, then we can also, we do not need to write them. And then we transform this into a conjunctive normal form or clausal form. We will do this step by step. So first thing, negation normal form. We have learned about special equivalencies, where I've told you that, for example, you can shift a negation inside braces. And this is what we want. We want to move the negations inwards of the logical formulas that we have. What we have to do, therefore, is, in the end, of course, we want to come up with a conjunctive canonical form, and a conjunctive canonical form also doesn't contain equivalences or implications. Therefore, we can remove them via the equivalences we have seen on the first slide, where we can transform an equivalence into 2 implications, and the implication can be transformed into a disjunction. Then you simply remove, additionally, all multiple negations. We also have learned that. And then all negations are placed directly in front of an atom. Take this example about the black and white penguins. You see here we have, of course, implications, and here another implication. And we want to transform this in the negation normal form. What we have to do here is, for example, first we have to look at the outer implication, which is this one, and we remove this one and transform it into a disjunction. But while doing this, the first part, of course, of the formula then has to be negated. And then we have here the inner implication, and there also we remove the implication with a disjunction, and the first part of the disjunction has to be negated. So next thing we have to do is remove all these negations inside the braces. And by doing that, for example, just consider the first one. So the first negation here is inside, it's no problem. This one has to be placed inside. For doing that, for example, we have first to put it behind the first brace. Therefore, the first conjunction will transform into a disjunction. And then we have to move this again over the universal quantifier into the next braces, and therefore the universal quantifier changes into an existential quantifier. And we have here inside not penguin becomes penguin, and the second one becomes not black and white, and the former disjunction becomes a conjunction. Simply try this out as an exercise, and in the end you will see you will come up with a formula where you only have conjunctions and disjunctions. Of course, you have also quantifiers, and you have the negation inward or inside the braces. So this is the negation normal form. Okay, next step, the prenex normal form. Therefore, we simply have to clean up the formulas. It means the quantifiers, you see here, they are all bound to the same variable. To clean it up, we bound it in each single part of this formula to another variable. So here we take x, for the second part here we take a y, and for the third part we take a z. And by doing this, then we have a unique identification that this quantifier denotes variable z, and this formula relates to the quantifier here. And the reason for cleaning this up is simply we want to put all quantifications in front of the formula while not losing its connection to the formula where the quantifier is applied to. So the next thing we can do is we have this formula, and then we put all these quantifiers in front of the formula. And you see the existential quantifier with a variable x, of course, refers here to the first part. Y refers to the second part. Z refers to the last part. So Prenek's normal form is pretty simple. Next step is the Skolem normal form. Skolem normal form is called after the Scandinavian logician Thoralf Skolem. And it's about the removal of existential quantifiers. If we consider our example, we can see here two existential quantifiers. And to remove them, we have to consider their position, because we know we cannot simply change universal and existential quantifiers, because this also changes the meaning of the formulas behind them. So if we have an existential quantifier that is independent of any other quantifier because it precedes all other universal quantifiers, then we can simply transform this variable here and the quantifier by a constant. On the other hand, if we have an existential quantifier and we have a universal quantifier in front, we only can remove it not by a constant, but it's dependent, of course, of this variable and of this universal quantification. And therefore, we only can substitute it by a function of this variable. So the Skolemization works in the following way. You can get rid of both existential quantifiers simply by removing the first one with a new constant. It's called the so-called Skolem constant. And the second one here, because one universal quantifier precedes this existential quantifier, this then can be substituted by a function of the variable of this universal quantifier. If there would be more than one universal quantifier in front, then all of the variables of the universal quantifiers must be represented within this function, the so-called Skolem function. So in general, it goes as follows. Skolem normal form, the algorithm for removal of all existential quantifiers from left to the right. So you start left and go right. And the rule is if there is no universal quantifier left of the existential quantifier to be removed, then the according variable is substituted by a new constant symbol. And on the other hand, if there are n universal quantifiers left of the existential quantifier to be removed, then the according variable is substituted with a new function symbol with arity n, so the number of universal quantifiers that are in front, whose arguments are respectively the variables of the n universal quantifiers. Let's have again a look on our example. So here you see the first one is substituted by a new constant a, and the second one with a z is substituted by a function of the variable y of the universal quantifier, which is in front. So now we have a formula that only contains a universal quantifier. What to do next? So now there are only universal quantifiers, therefore we can remove them. So we have a formula then without any quantifiers. What you do next is, to get into the conjunctive normal form, you should take here, for example, the formulas for distributive law that can be applied to switch this formula here into a conjunction of disjunctions, which would be then the conjunctive normative form or clausal form. So Here again is our example. I do not want to go in detail, but we apply distributive law and we apply De Morgan's law simply to achieve then a conjunction, these are the blue conjunctive symbols, over a set of disjunctions that we have here. And what you see here, what happens is the formula gets bigger and bigger. But this is not a problem whenever a computer does this. But of course, you should also be able to do this on, with a pen and on paper. So this, you will agree, is difficult to read because you have to consider here the conjunctions and the disjunctions. And you can also write this, of course, with the curly braces. And then you have here a set of clauses, a set of disjunctions. And you see here we have 1, 2, 3, 4 clauses in this clausal form that we have to consider. Okay, now let's take a look at the properties of the canonical forms. As you might have noticed, the canonical forms, they have been produced by the application of equivalencies, with one exception, and the exception is the so-called Skolem normal form. So between f and g, it means f is a formula and g is the prenex form, there are only equivalence transformations. Therefore, both of them are equivalents. Whenever f is true, then also g is true. The same holds for the relation between the Skolem normal form and here the clausal form, because in this transformation we also only apply equivalence transformations. Therefore, h, which corresponds to the Skolem form of our formula, and k, which corresponds to the clausal form of our formula, they both are equivalent. It means whenever h is true, then also k is true. The only difference is here between the prenex normal form and the Skolem normal form. They are not equivalent. You remember we have there made substitutions, a universal quantifier by a constant, an existential quantifier by a constant or by a function. Therefore, it doesn't hold that whenever f is true, that also k is true. So they are not equivalent. But of course, they are closely related with each other. So there is another connection. And it goes vice versa. It holds that if f, the original formula, is not satisfiable, it means if f is a contradiction, then also k, although it is not really equivalent to f, must also be a contradiction. So the contradiction is maintained through this transformation. And this is the basis or the foundation of the so-called resolution. And the resolution is a method that we will learn about in the next section of the lecture. That is an automated method that enables us to prove that a knowledge base is correct.